So this is Minor Class Connect sessions are recorded and distributed for learning purposes that are listed here. As always, be respectful, appropriate, and use and participate fully. Please don't share personal information during class for your own security reasons, just to keep you safe. All right, so here we go. We are on the board right now. You got a bunch of different brain stretches you can do. So the first one is, in which substance do particles move faster according to the kinetic theory? Warm, hot, or cold water? Remember back to our video that we watched with the different temperature waters and how fast the dye moved, the food dye moved. And then temperature measures the blank amount of kinetic energy that a substance's particles have. Is that the average or total? Remember we talked about the human populations with the same amount of dogs, which population's happier? That had to do with temperature. Which one will have a higher temperature? A bucket with 50,000 joules of heat energy or a cup with 50,000 joules of heat energy. So bucket, cup, or they're the same. And let's see here, heat only moves from cold to hot or hot to cold. Circle whichever one's correct there. And then you do have some matching here. So what is conduction? Think about a conductor has to hold their baton. What is convection? Think about how a convection oven has a fan. And what is radiation? Think about how the sun, heat energy can reach us through outer space, even though there's nothing in outer space. So you have definitions over here. Go ahead and match those up. Take about 60 seconds, work on all of these. And I'm going to go ahead and see who is working on the board. Looking good. I see Vanessa on the board, Kimberly on the board, Nichelle already jumping in there. Looking good. Get your answers up on the board. You can circle, you can match. You have lots of different options. Try to at least answer a couple of them to get your brain started today. Always hard to get our brains started, so let's get it done. Yeah, I know. My entire computer is having some issues today, so I'm sorry about that, Sean. I don't really know why. I probably just need to restart my computer and update it or something. Yeah, so I turned off the video just to make it a little bit easier so it doesn't lag as much. Yeah. All right, looking good. Get your answers up there. Going to give you about 10 more seconds. Match those up for me. And then we're going to go ahead and get started going over these. All right, perfect. Thank you. I see so much participation up there. Awesome. Let me go ahead, pause your tools, and I'm going to go ahead and start going over these answers. So which substance do particles move faster according to the kinetic theory? Definitely in hot water. Remember that hot molecules move faster. According to the kinetic theory, hot molecules have more energy and therefore can move faster, which is why food dye, when placed in hot water, spreads out a lot quicker. Temperature measures the average amount of kinetic energy that a substance's particles have. Remember, we talked about the difference between total heat. So total heat is just the total amount of energy. And this is like the total amount of dogs, right? Whereas temperature is the average amount of energy that each molecule, each particle gets. Each particle gets, right? Which is like how we talked about how in a big population, on average, people get less dogs per person, whereas in a small population, they get more dogs per person, right? Making them happier. Smiley faces if you guys remember that. And this has to do with the bucket versus cup, right? So in terms of temperature, the one with a higher temperature is the one that's smaller, because on average, each particle gets more of that total heat. Right, so same thing with a small population of dog lovers. On average, each person gets more dogs. Okay, so that's why this one's hotter in terms of temperature. Heat only moves from hot to cold. Remember, cold is just the absence of heat. So you can't have things move from cold to hot because cold's not a real thing, right? So it can only move from hot to cold. And then look at our definitions here. Yes, conduction, much like a conductor must touch their baton. It is due to when objects are touching, the collision of particles will transfer heat from the hot object to the cold object. Convection says that warm fluids will rise, right? Hot air is less dense and therefore goes up, whereas cool fluids will sink. Cold air is more dense and will go down, and this will create a bunch of swirling, which creates currents, much like a convection oven has a fan that helps create currents and make more even heating for whatever you're baking. And then radiation is the special one. I remember that because it starts with a different letter, obviously. And radiation is super interesting because radiation actually allows you to get heat energy without it ever needing particles, right? So conduction needs particles to touch. Convection needs particles to swirl. Radiation does not need particles at all. It can travel through outer space, empty space where there's no particles because it uses something unique called electromagnetic waves, which is why heat gets from the sun to the earth, even though there's no material, no substances in between. So this one's really special because without this, the earth would not be here. Go ahead, give me a smiley face, everyone, if you feel good about these. All right, looks like we did really well on these, so this is awesome. Great. All right, everyone. So this is going to be helpful because it's going to help us do our lab today and understand our lab today. But first off, I do, again, want to make sure that you open up your attendance check. All right, so link is in the chat box and the start of class word is right underneath that link. Make sure you give me green checks. Alejandra, Chris, David, Aqua, Jarrett, Janice, Jorge, Julian, Sean, Susan, Travis, green checks. Once we have that open and the start of class word filled out. Perfect. All right, so we are officially, sorry, this should say we are on day, I believe, 25, which means we only have 20 days left of the quarter. All right, give me a smiley face if that makes you happy. Give me a thumbs down if that makes you nervous. All right, I know it's ending really, really, really fast. All right, so there are only 20 days left. And again, courses are only a quarter long at our school. So after 20 days, courses are over. You can't submit anything else. So it's going by really quick. So you can see here that today we're wrapping up Unit 5 with our 5E lab. So I'm glad you're here. This is actually the easiest lab in the entire quarter, and it's still worth the same as all the other labs and exams. So it's really worth it to do this one well because this one will boost your grade really easily. Again, it's a super easy lab. And then we will be working on Unit 6 for the rest of the week and then starting Unit 7 on Friday. So we've been talking all about energy and its effects. We talked about how energy can change, potential versus kinetic, and today our lab is continuing our discussion on how heat moves. Awesome, Juliana. I'm so happy about that. I want to remind you guys that you have had 2 exams due. And remember, with your exams, as long as you do your best on the exam and complete every blank with a reasonable answer, you automatically get a 50%. Remember, that's my policy on exams is as long as you try it, you automatically get a 50%. If you try it and do well, then obviously you get a higher grade. But it's always in your best interest to try every question and to try to do it well, okay? All right, so we are talking today, we're going to continue discussing how heat moves. We already did our brain stretch on that, so I'm pretty confident you guys are pretty good with that. We're going to talk a little bit again about conductors versus insulators. Remember, conductors are good at conducting heat. Insulators are not. And then we're going to determine the ideal materials for an insulated thermos, so something that helps prevent the transfer of heat. Okay, so at this point, I'm going to go ahead and send you your lab link. You don't actually need to open it right now. It'll be more important once we actually open up your instructions. But just in case you want to open it, you can. Otherwise, I recommend just taking pictures throughout class. Give me a smiley face if that link is working. Confusion face if you're having issues. Again, you don't have to open it right now, but I know some of you want to, so you totally can if you want to. Cool. All right, sorry, again, I will be giving you the instructions for the lab step by step. I do the lab in front of you again in the recording, so you'll just need to be getting the data from the recording. So I'll go over that again in a few moments, but let's review. So remember, kinetic, what does the word kinetic mean? At this point, we've learned 3 different terms that include the word kinetic. So tell me, what does the word kinetic mean? Yes, absolutely. The word kinetic means motion. So kinetic theory is therefore the theory that the motion of particles in a substance are what heat is, right? So hot objects have fast particles, lots of motion. Cold objects have slow particles, very little motion. Now remember, even in cold objects, do the particles ever completely stop? Yes or no? Tell me in the chat box. Even in really cold objects, do the particles ever? Correct, right? So all particles always have some motion. It's just that the really slow ones are colder, the really fast ones are hotter. Now remember, conservation of energy, what does conserve mean? We had a synonym for conserve that starts with an S, or you can tell me a different word if you think of a different word. What does conservation or to conserve? Yes, absolutely. It means to save. So conservation of energy means that energy is saved. Energy in the entire universe, exactly, Julian, has always been the same. So there's never more energy created. There's never energy that's deleted or destroyed from the universe. Instead, it just gets changed. Remember, heat energy is never really lost. All right, heat energy just moves or changes. So for example, conduction, which is the main one we're going to be talking about today, we talked about this during our brain stretch. Conduction is the collision of molecules in touching objects that helps to transfer heat, right? So when objects are touching, the particles go from the hot object to the cold object, colliding, and those collisions transfer the heat. All right, give me a thumbs up, everyone, if that makes sense. Thumbs up if that makes sense. Right? So if you take a look at this diagram here, we actually learned about all of these different types, right? So radiation, for example, from a stovetop or from a flame will work without particles, right? You would still feel the heat from a fire even if there were no particles between you and the fire. Convection, right, is from the swirling of hot water rising, cold water sinking, and conduction, right, is from touching. So this handle will get hotter, and if you touch the handle, the particles from the handle will begin to collide with your hand's particles, transferring that heat, making it really hot. Again, moving from hot to cold. All right, so let's go ahead and talk about conductors versus insulators. Again, conductors, do you think that these are going to be good at conducting or bad at conducting? Let's take a look at our context clues. Conductors, good at conducting or bad at conducting? What do you think? Everything, when we're thinking about taking exams, state testing, right? If you can understand the words and break them down, it will really help you. So always think about how can I break down the words and understand what it means. Yeah, so conductors are good at conducting. Good at conducting, which we learned, right? Conducting is the transfer of heat. So they're good at conducting, transferring heat. They speed up the transfer of heat. Now, insulators, on the other hand, are the opposite in that they slow down the transfer of heat. Can insulators completely stop the transfer of heat? Tell me in the chat box. Can insulators totally stop the transfer of heat? No, remember that, again, all molecules move even a little bit, and just that little bit of motion means that eventually they will eventually transfer any heat that there is. So insulators slow it down, but they don't completely stop the transfer of heat. All heat will eventually move and will eventually be transferred. And we talked about the differences, right? Insulators tend to be things like wood or glass or cardboard or rubber. Those are all good insulators, meaning they slow down the transfer of heat. And conductors are things like aluminum, metals, right? Those are going to be good conductors, okay? So let's go ahead and take a look right here. What differences do you see between the ice cube on the left versus the ice cube on the right? Tell me in the chat box. What do you notice between the ice cube on the left and the ice cube on the right? Any differences that you see and what's happening? What scenario they're in? Yeah, so the left is definitely melting. Help, I'm melting. Melting. And the one on the right, so the one on the left is melting. What about the one on the right? Yes, the one on the right is not melting. At least it's not melting yet. Again, we do know that eventually it would, because all heat eventually transfers. Okay, what do you notice? But why is one melting and why is one not yet melting? Yes, exactly. So the one on the right has something between it and the hot plate, right? So this right here is a hot plate, meaning it gets hot, right? So we definitely have some aluminum between the hot plate and the ice cube. But what did we just say about aluminum? Is aluminum an insulator or a conductor? Is aluminum an insulator or a conductor? Yeah, it is actually considered a conductor, but you can see here that it is slowing down the transfer of heat as opposed to just it being completely on the actual hot plate. So here's the idea, guys, that really it's a range, right? So there's really a range of how well things conduct versus insulate. So some are good conductors, but will still slow down heat transfer a little. And some are good insulators, but will still eventually transfer heat. Okay, so it's all just kind of a scale or a spectrum, right? So it might be a good conductor versus a bad conductor or insulator, but it's all kind of on a scale. Okay, give me a smiley face if that makes sense. So even though it's a metal, again, it's not going to instantly transfer heat. It won't instantly transfer heat, just like a conductor can never, or just like an insulator can never completely stop heat. Okay? Cool. So that's what we're going to be taking a look at today. We're actually going to be doing a virtual lab. Again, I'm going to be showing it to you in the video. I do the entire lab for you. But in the video, you're going to see an ice cube placed on a bunch of different materials, and you're going to see how well it conducts versus insulates. Okay? And the whole idea of this, oh, sorry, let's go ahead and do this check for understanding really quick. Go ahead, circle the correct answers here. Conductors, do they slow down or speed up the transfer of heat? What about insulators? And which way does heat move? Again, that was our brain stretch. So taking that back to what we did at the start of class, as well as wrapping in our review. Oh, sorry, ignore this. All right, let me see who I've got participating. I see Nichelle, Janice, Lorelai, Kim, Vanessa, Hannah, David, thank you. Make sure, Jarrett, I see you. Awesome. All right, let me go ahead and pause the tools here and go over this. Yes, so conductors will speed up the transfer of heat, right? Again, will it be instantaneous? Will heat completely transfer right away? Tell me in the chat box, are conductors instantaneous? Right, so conductors speed it up, but it's still not instantaneous. Still not perfectly instantaneous. Whereas insulators will slow down the transfer of heat. But again, do they completely stop the transfer of heat? Yes or no? Do they completely stop the transfer of heat? No, right? So they slow it down, but don't completely stop it. And you guys are right. Heat, again, moves from hot to cold when we're talking about conduction. Perfect. Okay, so today in our lab, we're going to be taking a look at a couple different things. We're going to see what type of materials influence heat transfer. So we're going to be taking a look at some materials that are good conductors and some that are bad, meaning that they're actually insulators. And then we're going to talk about what materials would we want to use to create an insulated thermos. Okay, so what is an insulated thermos? How many of you have ever used a thermos, right? I think thermos might be the actual brand, but yeah, so here's what a thermos looks like. You've probably seen one of these. And what have you used it for? Tell me in the chat box. What have you put in your thermos and why? Yes, you can put hot soup in it. You can put hot coffee in it. What else can you put in there? Yeah, you could put water, hot water, or cold water. Yes. Now, why would you put those things in there? Tell me in the chat box. Why would you put those things in there? What's the point of a thermos? Oh, hot chocolate. Yes, hot chocolate is definitely a good thing to put in there. Yeah, it keeps it hot, right? So if it keeps it hot, do you think that it's made up of materials that speed up conduction, the transfer of heat, or slow down the transfer of heat? What do you think? Yeah, they're definitely slowing down the transfer of heat, right? So we're making materials where the heat just can't escape very easily, right? So we're slowing down transfer of heat, which means that this is made up of insulators, which makes sense because it's called an insulated thermos. Okay, the other thing I want you to think about though is that in an insulated thermos, you can actually also put cold things. So how many of you have ever seen the buckets that you dump onto the football coaches? Smiley faces, the Gatorade buckets that you dump on a football coach. Yeah, so what that is it's actually also made of insulated materials. It's actually just a giant thermos, and it's actually keeping the Gatorade cold. So either way, heat can't change, right? So either way, a hot liquid, the heat stays in, or a cold liquid, the heat stays out. Give me a thumbs up if that makes sense. So no matter what, heat just can't get through on either side. So it can't get outside of it, and it can't get into it, right? Perfect. So the thermos is made up of materials to help insulate it, slow down that transfer of heat. And again, in this experiment, we're going to look at some different materials and figure out which one will be best for a thermos. Okay. Now, what I want you to think about, tell me in the chat box. Okay. What do you think is going to be better for a thermos? Something where the ice melts really fast on top of it, or something that takes a long time for the ice to melt? Tell me in the chat box, what would be better for a thermos, an insulated thermos? because we're going to be melting ice cubes on top of materials. So which one's better? Takes a short time to melt or a long time? Yeah, absolutely, Jared. Absolutely, Antonio. Yes, the longer it takes to melt ice, the better the insulator, because it's slowing it down, slowing heat transfer down better. Down better. Give me a smiley face if that makes sense. Okay, so today you're going to be trying to figure out which ones take the longest before the ice melts, and those are the ones that you absolutely want for your lab. Okay, now what I want you to also take a look at is take a look over here. We have a Camelback insulated water bottle, and I want you to think, what do you notice about this bottle? There's something unique about this bottle here. Tell me in the chat box. What do you notice? Awesome. I see. And Michelle has an answer. Kimberly's typing. Yes, it has 2 layers to it, right? Smiley faces, if you can see that. You can see the dark blue layer and the light blue layer. Yep, there are layers to it. Now, what do you think might be between those layers? What do you think might be between those layers? Yeah, so absolutely, there could be air, right? So we have a double layer, and there could be air, or there could even be, right? There could even be a vacuum, which means that there's no molecules in there. Okay, so that would actually be a pretty cool one. So why is that important? So what I want you to remember is that air or gases, the molecules are actually more spread apart. So what do you think? If they're more spread apart, do you think it's going to be easier or harder to transfer heat? Much like if people are really spread about, is it easier or harder to transfer a message? Yeah, it's actually a lot harder. Remember that heat, right, gets transferred by collisions. And so if they're really spread apart, it's going to be hard for those molecules to transfer that heat. Okay, so things like gases are good insulators, bad conductors, right? Because the molecules are so far apart. They can't send the heat along very easily. Now, if it was a vacuum and there were no molecules, what do you think? Would that be a better insulator or a worse insulator? If there's no molecules at all to transfer the heat, is that a better insulator or a worse insulator? Yeah, it's going to be an even better insulator. Now, what I want you to know is that if you were to look at your windows in your house, some of your windows might actually be what we call double paned windows. And double paned windows actually use the same concept in this water bottle because you have 2 panes of glass. All right, and then in the center, you have air or a vacuum. And so this helps insulate your house and keep your windows from getting too cold or too hot and making your house too cold or too hot. All right, so if it's ever really cold and you put your hand up on the window and it's freezing, you probably don't have a well-insulated window. But if you can put your hand up against it and it's not as cold, it's probably doing better at insulating your house. Give me a thumbs up if that makes sense. So that's a practical application of both, like if you want to get a good water bottle as well as if you want to save money in heating or cooling your house, is to have good double paned windows. Excellent. All right. So here we go. This entire lab is actually completed for you in the recording. So where is the lab done? Tell me in the chat box. Where are we doing the lab? In the recording, okay? So you don't need a link to the lab report, to the virtual lab. I do it completely for you, okay? So all you need to do is you need to watch the recording, and I also highly, highly, highly recommend actually listen to the recording, okay? There are some parts that you can kind of get away with fast forwarding through because sometimes there's a lot of wait time. I understand that, but it's really good if you actually listen to it so that you can understand all the tips that I'm giving you to get a perfect score on this lab. Okay, so what you can see is in the lab, when I do it in the video, you'll see that you have 5 different materials: aluminum, glass, fiberglass, air between glass, we just talked about double paned windows, and brick. And what I will be doing is I'll be putting each of these 5 materials onto the hot plate, right? This is a hot plate, provides heat. We'll take some ice and we'll put it on top of the hot plate. We'll turn on the hot plate and the timer at the same time. And what you're going to do is you're going to wait for the ice to melt. The first one, the aluminum, I actually do for you, and when the ice melts, I actually pause the timer and I show you how to fill it into question 1 of your lab. Okay, give me a smiley face if that makes sense. I do the aluminum for you. You should get the exact same answer as me for the aluminum, because you should just copy it based on what you see. Now the next 4 though, I do not stop the timer. The next 4, you actually need to pause the video. Okay, give me a smiley face if that makes sense. For the next 4, you need to pause the video when you see the ice disappear. Okay? Now, you need to get as close as possible to exactly when the ice disappears, because I'm going to be grading you on as how close you are to the exact time. All right, again, I do the lab for you, so there is actually a correct answer and an exact time that is correct. So you have to make sure you're doing it as closely as possible for when the ice melts and disappears off of the hot plate. Okay, one more time, give me thumbs up if all of that makes sense. I do it for you. I show you aluminum. The other 4, you need to actually pause the video to get the correct time. Okay? Perfect. All right, so what I'm going to do is I'm going to be sending you the instructions. After every step, make sure you pause and complete it in your lab report. Okay, again, the lab is done for you. Listen to the audio. You can fast forward through a couple parts. I won't get mad at you for that, but for the most part, make sure you're listening to it, okay? And what you're going to see again is I'm going to put the material onto the hot plate, the ice cube on top. I'm going to start the hot plate and the timer, and your goal is to figure out how long does it take for the ice to melt. Do we have any questions before we get started? I will be sending you the video and you will begin working on this. Do we have any questions? Any questions? Yes, no, tell me in the chat box. You have a question, Aqua? Or do you mean you're good? Oh no, hey, Aqua, come on. You're just being silly. Yeah, so what we're going to do is you're going to work on the video and your lab, and then I will give you the end of word class a few minutes before class is over. So don't ask for the word until that point. Don't be like Aqua, who's being silly. All right, so here we go again. I just sent you the video in your chat box. All right, there's the YouTube video, and then for questions 1 through 3. And again, here's the lab, and I need you to go ahead and get started to work on that. Give me a green check if that's all working for you. And I'm going to start a timer for 10 minutes. Green checks if the video is working. Perfect. All right, I'm going to go radio silent. Get to work. Hello students, in this video I will be completing the entire lab in front of you. So all you'll need to do is watch and listen to this recording so that you can get all of the data from the video. So again, you don't actually need to open up the lab on your own. You need to just watch this as I do it, and you will get all the data as you watch and listen. All right, so again, as always, make sure you watch the instructions. After every step, pause and complete the steps in your lab report. All right, and I'm going to go ahead and show you how we're going to do this. Okay, so you can see in question number 1, we are going to be figuring out how long does it take ice to melt for these various materials. So here's the virtual lab. Again, you don't need to have this open yourself because I am doing this for you in front of you. Okay, so here we go. You can see we have 5 different materials here, as well as you can see that we have some other things. We have ice, tongs, a timer, and a hot plate. All right, so what I'm going to go ahead and show you is the basic instructions. So I'm going to give you the data for one of these, and then for the other 4, you'll just need to watch them and gather the data on your own. So again, I am doing it for you in front of you in this video though. So what we're going to do is we're going to use the tongs to place the material, in this case the aluminum, onto the hot plate. Now we're going to go ahead and grab some ice and place it on top of the hot plate. And what we're going to do is you're going to see that we are going to turn on the hot plate and the timer at the same time. And then we're going to wait for the ice to melt, at which point I will stop the timer for the aluminum. For all the future ones, I will not stop the timer. Instead, you will need to pause the video to figure out what time it stops melting. And that's on you to make sure that you do that correctly. And then we'll record the time in our table here. You'll see that the first dash is minutes, the second one is seconds, and the next one is milliseconds, which is the exact same thing we have here. Minutes, seconds, milliseconds. All right, so let me go ahead and zoom into this for you so that you can see it very easily. And we're going to go ahead and, sorry, let me scroll down a little bit, zoom in this way. All right, so we're going to go ahead and turn on the hot plate and the timer. And you can see that it begins to melt very quickly, which probably shows us that aluminum's not a very good insulator, which makes sense because aluminum is a metal, making it a pretty good conductor, not a good insulator. So again, for this one, I'm going to stop it as soon as I see the ice has completely melted. And there we go. So for this one, it's 0 minutes, 19 seconds, 77 milliseconds. So I'm going to go ahead and fill that in here, and you can copy that. So 0, 0, 19, 77. And in fact, I do actually recommend that you just delete some of these spaces so it looks a little bit neater. So 0, 0. So really just copy it exactly as you see it from the timer. So 0, 0, 19, 77. So 0 minutes, 19 seconds, 77 milliseconds. Okay, so that is the aluminum. So now what I'm going to do is I'm going to go ahead and show you the glass, fiberglass, air between glass, and the brick. Again, for these ones, I am not going to actually stop the timer for you. You are going to need to pause the video and stop it yourself. And you will need to fill in the data yourself. I will not be showing you the data for that. You need to measure it for yourself. Okay, so let's go ahead. Oops, sorry. Let me actually put the aluminum back, put the glass on. Drop that. All right, we're going to go ahead and grab another piece of ice, place it on top of here, and I'm going to go ahead and begin the timer, and you need to, and the hot plate, and you need to watch this as it goes. You can see that this one is definitely melting at a slower rate, which means that glass is probably going to be a better insulator than the metal that we saw, which again makes sense because metals are really bad insulators because they conduct heat so well. So we can definitely see that the glass is going to help slow down heat transfer, and it's going to be a better insulator than what we just did. So again, you're watching until the ice is completely melted, at which point you'll need to pause the video. I will not pause the timer for you. You will need to actually do it yourself. Looks like it's almost melted, so be ready to pause the video in just a moment so that you can catch this time on the timer right here. And pause. So make sure you pause the video, make sure you grab that time, and that time is what you should be putting in here. Again, you can just delete this, but please make sure you include all three parts, the minutes, seconds, and milliseconds. All right, so again, you should have gone back to when this completely melted, paused the video, and gotten that time. All right, again, I will not be getting that data for you. You need to get it from the actual video that I'm doing right now. All right, so that is the glass. Let's go ahead and do the fiberglass. Grab the ice, drop it on, and same process. I'm going to start the hot plate, start the timer. You need to pause the video when it's completely melted, and then you will record that time, minutes, seconds, milliseconds. Here we go. We can see at this point that this is definitely taking a lot longer than the glass. So again, this one is definitely better at slowing down heat transfer, which means that it's going to be a much better insulator than both the aluminum, which was really bad, as well as the glass, which was a little bit better, but this one is taking a lot longer. So again, you're going to keep on watching until this completely melts, at which point you're going to pause the video, and then you'll record that time in your lab report as you see it, minutes, seconds, milliseconds. Keep on watching. It will melt eventually, I promise. It does look like it's getting pretty close to melting here. So we're going to let it keep on going. And again, once the ice has melted, it'll disappear from the glass. And at that very moment, you want to pause the YouTube video, write down the time. Again, the time is going to be your minutes, your seconds, and your milliseconds. And that's what's going to go into your lab report for the fiberglass. This is the fiberglass for question number 1. So again, at this point, it's been melting for about 5 minutes. Again, this seems like to be a really, really good insulator. It's taking a very long time for the ice to melt. Probably going to be good for something that we want to keep our items cold or keep them hot, such as in our insulated thermos that we're going to be talking about. All right, just a few more moments. Again, get ready to pause the video so that you get the exact time. When this is being graded, you will be graded on how close you are to the exact time that the item was melting for until it was completely melted. So you will need to get as close to the exact time as possible to get a good grade on this. And this is 60 points of your grade to get this correct. All right, so at this point, it has just disappeared, so you should have paused the video, gotten this time. Again, you have minutes, seconds, milliseconds. So again, you want the exact time, and that's what you would fill in here for the fiberglass. All right, so I'm going to go ahead and reset that, turn this off, and let me go ahead and get this off. All right, so we just did the fiberglass. Now we're going to go ahead and do air between glass. Grab our ice, and just like last time, we are going to start our hot plate, start our timer, and again, we're going to wait until this is completely melted. You will need to pause the video. That's your responsibility. You need to get it as close as possible to get full points, and that is what you will be recording here for air between glass. So here we go. All right, so at this point, this is almost melted. So again, keep a sharp eye out. You need to wait until this has just disappeared from the plate, and you will need to pause your YouTube video to make sure that you get the exact time, minutes, seconds, milliseconds. Again, you have to be extremely close to the correct time in order to get credit. So make sure that you are ready to pause the video in just a moment. A few more seconds here, probably. And again, I will not be stopping the timer for you. You need to stop the timer, or you need to pause the video and get the exact time so that you can get your correct points. And looks like it's about to disappear. Be ready to pause. All right, so at that point, it just disappeared. You should have paused the video at that exact time. Again, I am not pausing it for you. You need to do that yourself, and you do need to get as close as possible so that you get full credit on this. If you are off by too many seconds, you will get a 0 on this part. So make sure that you are as close as possible for each one. All right, so I'm going to go ahead and, again, that should have been written for the air between glass. That was the one that we just did. Again, make sure you have minutes, seconds, milliseconds. All right, so let me go ahead and reset that, and we are going to go ahead and do our last one, which is the brick. Okay, pop that on there, pop the ice on there, drop that down, and we are going to go ahead and do this one last time. Hopefully this one's a little bit faster. Here we go. Sorry, let me try that again. Let me do the heat first. Here we go. All right, so this one is definitely melting very fast, similar to the aluminum. So it does seem like it is going to be a bad insulator. It is allowing heat to transfer too quickly. All right, so it's a bad insulator and it's going to melt really fast. So be ready to pause your video so that you get the exact time so that you can get the correct score on this. You have to get it exact. All right, so it just disappeared. At that point, you should have paused the video and you should have gotten the time. So please include the 00 for your minutes and then whatever your seconds and your milliseconds were. Make sure that goes next to your result for brick. All right, and I'm going to go ahead and reset that. And again, I did not give you the times at all. You need to have gotten them from the video. You need to get exact times. If they're not close to exact, you won't get points for those ones. They have to be as close as possible to exact. All right, so now what we're going to do is we're going to order the materials starting with the least insulating. Let me blow this up a little bit. The least insulating to the most insulating. So least insulating is 1, most insulating is 5. All right, so what this means is that the shorter your time is, the less insulating it is. So I do want to make a note of that really quickly so that you remember this. Here, let me write it right here for you. All right, so the shorter the time it took for the ice to melt, the more heat was able to transfer, the faster heat was able to transfer, making it a really bad insulator, as opposed to when it takes longer, the longer the time it took for the ice to melt, the slower heat was able to transfer, making it a really good insulator. Okay, so again, we want to keep this in mind. So what this means is that short times mean bad insulators, and that long times mean good insulators. Okay, so the ones with the shortest time, that's what's going to be 1. The next one with the next shortest time is going to be 2. Keep on going until you get the longest time, and the longest time you're going to label as 5. All right, so again, you want to look at your data. So look at your data and number them 1 as the shortest and least insulating to 5 as the longest time and most insulating. All right, and so you're going to order those, and you do need to get them all correct in order to get the credit for that. And then based on your results from the data, what 2 materials do you think would work best for designing an insulated thermos? Use actual numbers from your data. So again, the most insulating materials are going to be your number 4 and number 5. Again, make sure you order these correctly based on the directions I just gave. Okay, so short times are 1, 2, long times are 4, 5, medium time is 3. Okay, and then what you're going to do is you're going to type in the type of material. So for example, if you think fiberglass, glass, brick, air between glass, aluminum was the best at slowing down how long it took for the ice to melt, long times. All right, so you're going to type in that material. You're going to give me the actual result. Again, you have minutes is the first section, seconds is the second, and milliseconds is the third. So make sure you include minutes, seconds, and milliseconds. And again, if it's a good insulator, this should be a long time. So you should make sure you fill that in. And then do the same thing with your 4th ranked material. Again, 4th ranked and 5th ranked are the most insulating ones. So do the next material, which is the one with the next longest time. Again, include your result, And again, it should take a long time to melt, making it a good insulator. So again, these should be your long times. If they're not your long times, you've done it incorrectly. And at that point, you can submit, and it will ask you again if you want to submit, and you should be able to. All right, thank you everybody, and have a great day. All right, everyone. Go ahead, pause your videos, give me a smiley face if you're ready to listen. So hopefully you didn't notice that I accidentally got kicked out, but I'm back. All right, looking good. All right, so how are we feeling? Is it making sense so far? Are we having any issues? Tell me in the chat box, how are you feeling about those instructions? You're feeling good? Awesome, Micaiah. Let me know if you have questions. You're on break. Oh, awesome. Perfect. Okay, everyone. So again, make sure you fill these out. Again, I said several times in the video, make sure you get the exact times. So make sure you're pausing exactly when it finishes melting, and make sure you include both the minutes, even if the minutes are 0, the seconds, which are the middle ones, and the milliseconds, which is the last one. Okay. And then don't forget, you're going to go from least insulating, which are the ones with the shortest times. Those will be marked as 1, 2, 3. And then to the most insulating, which are the longest times, which you're going to mark as 4, then 5. All right, so 5 should have the longest time, and 1 should have the shortest time. It's the least insulating. And then again, for the first and second material that you're going to use for your insulated container, you want to use the ones that you ranked as 4 and 5, because again, those are going to be the ones that took the longest time and are therefore the most insulating. Smiley faces if that makes sense. I do go over that in the video, but I just want to make sure I emphasize it in class as well, just so you have that heads up. Awesome. All right, everyone. So at this point, we described how heat moves, explained the differences between conductors and insulators, talked about ideal materials for an insulated thermos. Go ahead on the whiteboard, point how are you feeling about those different objectives? How are you feeling about the lab? Very confused, still need help, pretty good, awesome. Excellent. I was glad you had lots of time to start the video today. That always helps. So make sure you finish that up. All right. So continue that lab report. Again, it's the easiest lab report, so I really recommend get it done today. It's also the easiest one for me to grade, so it will get graded really fast. So make sure you do that so that we don't have to enter zeros, because the zeros will be entered before the exam on Thursday. So get it done today or tomorrow as fast as you can. Okay. All right. So I'm going to go ahead and stop the recording here.